Hi guys, today's quick fire questions is on all things to do with radioactivity and nuclear fission. So with all my other quick fire questions, you simply need to listen to the question, press pause, have a go at answering the question, and then press play in order to hear my idea of a perfect answer. Let's start with, what was the plum pudding model? So the plum pudding model was the original model of the atom, and what it thought was that the sponge was made out of positive charge and that the plums were made out of electrons. Describe the gold foil experiment. So you're going to say that alpha particles were fired at very thin gold foil. Describe the results of the gold foil experiment. Well, first of all, most of those alpha particles passed straight through the gold foil. Second of all, some of those alpha particles were deflected a little. Thirdly, only very few of those alpha particles were deflected by a large margin. Link those results with conclusions that could be drawn from the gold foil experiment. So the fact that most of those alpha particles pass straight through the gold foil tells us that the atom is largely empty space. The fact that some of those alpha particles were deflected tells us that the nucleus is positive. And the fact that very few of them were deflected tells us that the nucleus is very small. So as an aside, clearly the plum pudding model was completely wrong, and the results of the gold foil experiment proved this, because what they showed instead is that an atom is made up of a very small nucleus surrounded by empty space effectively, which is where the shells of electrons circulate. Describe the mass and the charges of protons, neutrons and electrons. So remember that protons and neutrons both have a mass of 1. An electron has a mass of 1 divided by 2000. And in terms of charges, protons have a charge of +1, electrons have a charge of -1, and neutrons have a charge of nothing, because obviously they are neutral. What is a nucleon? Well, it is any particle found in the nucleus of an atom, i.e. it's the protons and neutrons of an element. Define isotope. An isotope is atoms of the same element with the same number of protons but different number of neutrons, and therefore they have different mass numbers. Describe the nature of an alpha particle. Remember, alpha particles are made up of 2 protons and 2 neutrons, i.e. they are a helium nuclei. This means that they have very large mass and they have a large charge. So what happens to an atom when it loses alpha radiation? So what happens to an atom when it gives off alpha radiation? Well, clearly its atomic number, its proton number, will go down by 2, while its mass number will go down by 4. So let's try an example. So we're having radium 222, which is its mass number. Its atomic number is 88. Now describe the new element formed together with its mass number and its atomic number when alpha radiation is given off. Now, because it's lost 2 protons and 2 neutrons, its mass number will go down by 4, so it will become 218. Because it's lost 2 protons, its atomic number will go down by 2, so that means it will be 86. This means it's a new element, and that element is radon. Describe the nature of a beta particle. Well, that is that it's a fast-moving electron. Remember, what happens in this case is that a neutron turns into a proton and stays within that atom. So what will happen when beta decay occurs? Well, the mass number will stay the same because a neutron simply turns into a proton and they both have a mass number of 1. However, the atomic number, the proton number, will go up by 1. So let's take an example. So carbon 14, so its mass number is 14, its atomic number is 6. So when beta decay occurs, describe the new element formed. Right, because the mass number is unchanged, we'll still have a mass number of 14. However, the proton number will have gone up by 1 to 7, so you're going to have a new element, which is nitrogen. Describe the nature of gamma radiation. Well, gamma radiation is really different to the other two because it's just an electromagnetic wave, so you don't see any change in mass number or proton number for that matter. Describe the penetrating powers of alpha, beta and gamma. Remember that alpha is least penetrating and is stopped by paper. Beta has intermediate penetration powers, so it's stopped by aluminium foil. Gamma is very penetrating and therefore is stopped by several centimetres of lead or meters thick concrete. Describe the range in air of alpha, beta and gamma. Remember, alpha only has about 10 centimetres penetrating power in air. With beta you're looking at about 5 to 10 metres, and gamma is infinite, so it'll just go on and on and on. Describe the relative ionising powers of alpha, beta and gamma. So alpha is the most ionising, beta is intermediate, gamma is the least ionising. What does ionising radiation actually cause? Well, it causes atoms to become ions, so to either gain or lose electrons. What is radiation measured in, i.e. what's the unit of radiation or radioactivity? That is the Becquerel BQ. What is background radiation? Well, it's radiation which is always present. Give some sources of background radiation. Those are cosmic rays, radon gas, food, medical sources, and things like granite rocks which you find in Cornwall. What is half-life? That's the time taken for half the radioactive nuclei to decay. Now I'm going to give you an example of a half-life equation which you can have a go at to check your understanding. Give some properties of radioactive traces used in medicine. First of all, they need to decay to a stable product. Secondly, you don't want them to have too long a half-life because they'll be making radiation occur in your body, which is dangerous. Thirdly, the half-life needs to be long enough so you can actually monitor what it is you're after. So for example, the kidney. Describe the use of beta radiation in aluminium foil thickness. This is a weird one to describe, but just remember you fire beta radiation at some aluminium foil and there's a sensor on the other side of the foil. If the count rate is too low, it tells you that the aluminium foil is too thick, so it sends a signal to the rollers to press together to make that aluminium foil thinner. Describe the use of alpha radiation in smoke alarms. So remember with smoke alarms, that alpha radiation is given off and there's a detector a few centimetres away. Now what happens is the alpha radiation ionizes the air, creating a small current which is picked up by the detector. Now if there's smoke, remember alpha isn't very penetrating, it stops the alpha particles ionizing the air. So what happens instead is you can't pick up that electrical charge anymore, and so no charge means there's a fire apparently. Describe dangers associated with alpha, beta and gamma. Well, obviously they're ionizing radiation, which means that they're carcinogens, mutagens, which means they cause cancer and mutations. So yeah, anything like that. How do you lower your risk of receiving ionizing radiation? First of all, you limit your exposure time. Secondly, you wear photographic film, which will pick up how much radiation you've been exposed to. And other sensible things are to hide behind lead shielding and to wear gloves and lead aprons and tongs, and use tongs, etc. when handling the radiation. Describe the use of gamma radiation in detecting water leaks in pipes. So what they do is they add a gamma source to the water, it flows, and there's a detector above ground which is monitoring the levels of radiation. If that radiation increases massively, it tells you that there's a big pooling because there's a leak at a certain point, so all the water's pooling out, it's escaping, which means you get a much higher reading. Now we're moving on to nuclear fission. So first of all, define nuclear fission. Be very specific here, it's the splitting of an atomic nuclei. So describe the process of nuclear fission inside a nuclear reactor. So one neutron is fired at a nuclear fuel such as uranium. That uranium fuel, the nuclei split, forming two daughter nuclei. 2 to 3 neutrons are given off. They go and hit other uranium nuclei, and before you know it, you've got a chain reaction. Describe the setup of a nuclear reactor. So remember, first of all, you've got lead shielding, or you've got concrete shielding around the outside to prevent radiation escaping. You've got control rods which dip down into the nuclear reactor, and what those do is they absorb some of the neutrons. You've got a moderator which slows down the neutrons, removes some of their kinetic energy, and the same with the coolant, that removes some of the energy from the reactor because you're trying to make it much safer. Describe how electricity can be generated from a nuclear reactor. So remember, first of all, is that that chain reaction that's set up creates a huge amount of thermal energy. The thermal energy heats water to make steam. Steam turns a turbine, and the turbine turns a generator. And the generator makes electricity. Right, that's everything I wanted to say. I hope you found this video helpful. I'll try and make another quick fire question soon. Good luck with your revision, guys. Bye!